It's about to get freaky. Gargantuan tube worms, foot-long clams, shrimp with eyes that can detect radiation. And I'm not talking about the special at Red Lobster. These are just a few of the stranger-than-fiction creatures you can find in the deep, dark depths of the ocean. The ocean is teeming with life, even its most hostile parts. It fosters the most spectacular and diverse life forms imaginable, including us. Just because we live on land doesn't mean we're not homies with our salty neighbors, okay? So how does she do it? What makes the ocean so lifey? Hi, I'm Sage, and this is Crash Course Geology. The ocean! More than 70% of our planet is covered in this enormous, salty, plankton-filled wonderland. Seriously, there's a lot of plankton in there. We've been fascinated by this massive body of water for centuries. One of the earliest studies of the ocean started in 1872 when the British HMS Challenger hit the seas for a 1,250-day journey that covered over 68,000 nautical miles. You could consider it an early feat of oceanography, the study of physics, chemistry, biology, and geology of the oceans. Later, tools like sonar, submarines, satellites, and submersibles let us gather data from above and send stuff below. Everything from cameras to robots to Titanic director James Cameron. Voluntarily, of course. He was really vibing down there. So today, we know quite a bit about the ocean. And it isn't just one uniform mass of salt water. Some parts are way saltier than others, or way hotter or way colder. Some parts are home to thousands of species, while others support almost none at all. And when it comes to the seafloor, it's not just flat and sandy. There's a lot going on with the ocean's bathymetry, or the topography of the ocean floor. Now, I can't take you on a tour of it. The crash course budget is a little too tight for a full-on submersible, but I bet I know someone who would make the trip. Dwayne, you want to go on a little adventure? Dwayne starts his journey on the coast, where the land meets the sea. As he strikes out onto the seafloor, he'll roll along the continental shelf, a part of the ocean floor that's still continental crust. It's stretched out and topped with a thick layer of sediment accumulated over thousands of years. Continental crust is thicker and more buoyant than oceanic crust, so it floats higher on top of the mantle. Combined with the thick layer of sediments, the ocean is shallower on the shelf, usually less than 200 meters deep. Here you'll find algae, seaweed, and tons of different kinds of fish and sea creatures. Oh, hey look, Dwayne found Nemo. From here, things go downhill fast. That's the continental slope, the transition zone between the continental shelf and the deeper basin of the ocean. It's made of thinner, denser oceanic crust. A few kilometers under the surface, it starts to smooth out again, in an area called the continental rise, a zone of sediments accumulated at the base of the slope. And when Dwayne hits the end, he'll find himself in the abyss. Or at least the abyssal plain. No, don't worry, pal, you have location sharing on. We won't lose you out there. The abyssal plain is the flat-ish bottom of the ocean basin. It's mostly made of volcanic rock called basalt and covered in a layer of sediment. It tends to hover around 4.5 kilometers deep. Here, it's hard for much of anything to survive. It's cold, it's dark, and the pressure is up to 600 times what it is on the surface. It's okay, Dwayne can handle it. Regardless of where you dive in, there are plenty of cool landforms to explore under the sea. Like submarine canyons. When the sea level's low, they're carved by rivers cutting through the continental shelf and slope. Then they're deepened by submarine avalanches called turbidity currents. And there are underwater volcanoes called seamounts, where violent submarine volcanic eruptions built up mountains on the seafloor. You'll find lots of unique sea life here, from bubblegum coral and squat lobsters to loggerhead sea turtles and rare sei whales. All right, buddy, time to come to the surface. Come on out of the water. Now, Dwayne just took a trip along a passive margin, which is where the continental crust meets an oceanic crust on the same tectonic plate. Pretty chill. But if he had toured, say, South America's western coast, he would have found a much narrower continental shelf at an active margin. That's the edge of a tectonic plate where lots of earthquakes rattle the seafloor. Yeah, I'm not going to put you through that, bud. And there are other things I'd worry about if Dwayne had kept wandering the bottom of the ocean, like hydrothermal vents. They're underwater chimneys as high as 55 meters that send up blackened plumes of particles and water hot enough to melt solid metal. Can you imagine if that's what happened when they picked a new pope? Hydrothermal vents are created by plate tectonics, the theory that Earth's outermost layer is broken up into chunks, called tectonic plates, that move across the mantle. We got way more into plate tectonics in an earlier episode, but the important thing to note today is that it plays a big role in marine geology. One place hydrothermal vents form is where oceanic plates pull apart. Here's how that happens. At these divergent boundaries, lava erupts in the gaps and then cools and hardens into new oceanic crust, or seafloor. All that tectonic movement can crack deep fissures in the crust, where water and magma mix. The liquid heats up, dissolving minerals from the surrounding rocks. And when that superheated fluid comes back up and meets the frigid temperatures at the seafloor, the minerals form stubby spires and towering chimneys, and voila, a hydrothermal vent. You'll find a lot of them along underwater mountain ranges called mid-ocean ridges. Hydrothermal vents pump heat from deep in the earth into the oceans, creating hot, mineral-rich zones for super weird creatures to call home. That, and the fact that these vents are often so deep in the ocean that there's no light for photosynthesis. Instead, bacteria are chemosynthetic, meaning they feed on the chemicals from the vents, and they serve as the base for the food chain there. 2-meter-long tube worms, orange-shelled mussels, and fuzzy crabs all happily thrive around hydrothermal vents. Marine geologists study these ecosystems to try to figure out how life began on Earth and how it might exist on other planets. Like, some research has found primitive microorganisms living by hydrothermal vents, a sign that life could have started in those environments. And if chemical-eating organisms can exist in hostile Earth environments, maybe they can survive elsewhere in the solar system too. Hydrothermal vents can also form at convergent boundaries, where a continental plate and an oceanic plate collide, plunging one into the mantle beneath the other. That process creates a trench, which forms as one plate dives beneath the other, bending the seafloor to create a deep V-shaped depression. And if that happens with two oceanic plates, the trench is massive. That's how we got the Challenger Deep, the deepest point in the world, located in the Pacific's Mariana Trench. It reaches nearly 11,000 meters below sea level, so deep that Mount Everest could fit inside with room to spare. Well, at least that's how deep we think it is, because it turns out measuring it is surprisingly difficult. Since the HMS Challenger, we've been trying to measure it, starting with a weighted rope and then graduating to sonar technology in the 50s. The most accurate estimates as of filming in 2026 came from a series of submersible dives in 2020, which clocked it at 10,935 meters deep. But it's hard to know for sure. We can't exactly drop a yardstick down there to get an exact answer. What we do know is that, just like at hydrothermal vents, life exists in deep-sea trenches. And that life is weird, with a capital W. We're talking transparent sea cucumbers, saucer-sized single-celled organisms, and shrimp-like critters that eat sunken wood? But the ocean's geology doesn't just create hotspots for life on the seafloor. It affects life everywhere on Earth, especially through currents. Currents are continuous, directed oceanic movements that carry water across the globe. They're driven by wind, water density, tides, and Earth's rotation, and they're affected by bathymetry, which can change their speed and direction. For example, about 3 million years ago, tectonic shifts formed the Isthmus of Panama, which connected North and South America. This stretch of land deflected the warm, salty ocean current that once flowed through the gap. It redirected that water northward, which warmed up Europe. And currents can have a cooling effect, too, like when Antarctica broke off from South America. This allowed frigid waters to circle the continent, creating a barricade for warmer waters and chilling Antarctica into the frozen landscape we know today. One of the most important contributions of ocean currents is the distribution of nutrients. Upwelling currents bring nutrient-rich waters from deep in the ocean upward to feed microorganisms at the base of marine food webs. Currents can even move animals themselves, like a watery superhighway, distributing populations of everything from plankton to fish eggs to sea turtle hatchlings, influencing how these creatures evolve. Oceans pump tons of water around the globe in a so-called global conveyor belt of currents, mostly driven by changes in temperature and saltiness. Basically, water that's saltier and colder is more dense and sinks, traveling along the deep ocean bottom, while water that's less salty and warmer is less dense and upwells. But as we unleash greenhouse gases into the atmosphere, Arctic temperatures are warming, which means ocean waters are cooling slower and glaciers are melting faster, flushing fresh water into the mix. All of that slows down the conveyor belt. The ocean also acts as a huge carbon sink, storing carbon dioxide so that it doesn't warm the atmosphere. That's a massive deal for a lot of reasons, like the temperature of the Earth determines what kind of creatures can live here, including us, But as surface water warms and currents slow, the surface waters saturate with carbon dioxide and can't absorb any more. Many scientists recommend cutting carbon emissions to prevent large-scale disruption of currents and ocean environments. You can learn more about that in Crash Course Climate and Energy. Earth's oceans are still full of mysteries. As of June 2024, we've only mapped about a quarter of the world's seafloor in high resolution. That means there's a whole 3/4 that could still be hiding even more creepy little Earth aliens. Dwayne wants to see more of those fuzzy crabs. The ocean is much more than a big pool of salt water. And the seafloor isn't just an underwater sandy beach either. The bottom of the ocean is a maze of slopes, trenches, and formations that show us plate tectonics in action. It creates habitats for creepy creatures and affects the currents that are essential to Earth's climate and life. Our planet wouldn't be the same without it. In our next episode, we'll tackle volcanoes. See you then. Thanks for watching this episode of Crash Course Geology, which was filmed in our studio in Indianapolis, Indiana, and was made with the help of all these nice people. If you want to help keep Crash Course free for everyone, forever, you can join our community on Patreon.